Welcome to Advanced Aliasing in C. My name is Timothy Lattis, and this is the Neo Kino Graphics channel. Let's start with some background. Why do we include the full API when we only use a small subset? I don't like to include stuff. I prefer dependency-free. Instead, I rewrite the necessary includes in the file itself. However, I'm always looking for a way of making that easier. Second point, complex type systems are typically pure overhead. The hardware has registers and instructions. I only need as much type information as is required to describe what instructions are desired. I'm always looking for ways of reducing language type pollution. There's a second problem that C often defaults to the wrong types. For instance, signed, when unsigned defaults is actually required. You'll note on x86-64 we have transparent unsigned 32-bit to 64-bit typecasting. It's in the hardware. Integer registers in x86-64 are 64 bits. 32-bit variables and registers are technically still 64 bits. They're just using the lower 32-bit. Normally 32-bit ops on x86-64 is 0, the upper 32 bits. There are some exceptions. Vendor-specific behavior, for instance, the behavior of BSF and BSR with 0 input. However, other than those, you can use this generically. So a typecast from unsigned 32-bit to unsigned 64-bit is free. This holds if the value is already in a register. This is also why one should default to unsigned for integer. Now, aliasing is very common on x86-64. It's something you should be doing a lot in your code. For instance, if you're working with signed numbers and you want to check whether they're less than 0 or greater than a certain value, you should be doing that with one unsigned operation. This is because the signed values fill out the upper half of unsigned numbers. So it's better just to do one operation to check both conditions. This is one of many examples. Here's a review of how I like to do types. I set up a bunch of type defs. I use signed only at the micro-op when I actually need it. Otherwise, I default to unsigned. My type defs always start with one character, the type, B for byte, W for short, I for int, L for 64-bit, F for float, D for double, followed by the number of components. Typically they're all 1. However, I do alias the same types in C and in GLSO, so I often use 4-vector or 2-vector in GLSO. Sometimes I use a 4-vector in C, for instance if I want SSE ops. You'll note before that my type def includes attribute vector size. That is how you do it in GCC. So I always default to unsigned, and I promote to signed at the operation. It's easiest to just use unsigned integers all the time, similar to how you would with a register. So for an example, if I want a minimum of 2 unsigned integers, I create a function, an inline function for that. I use min si1, so minimum of signed integer 1 component, and all the arguments are unsigned. Only inside the code do I typecast to signed for the compare operation. And you'll note when I clean this up in my short form, you get something very concise. I underscore for static inline, I1 for unsigned int, and then si1 underscore to do the type def to signed. Now I'm reviewing how I commonly do pointers. Note in the past I used to use R and V for restrict and volatile, and I'd have that on the end of the type. Since then, I typically moved R and V to before the type for the macros and for the type defs. I find that this is easier to understand. One issue with C is that if you want to use restrict or volatile, you have to remember which side of the pointer to use it on. Restrict typically goes on the right side of the pointer. Volatile goes on the left side. I don't like to have to remember this. Of course, I do type defs, so I don't have to remember this. I also create a bunch of defines to do fast typecasts, so I don't have to do parentheses out. It removes one level of nested parentheses. So I have the type with the underscore, and that makes it quite simple. All my pointers are kept as unsigned 64-bit. This is the way pointers are in the registers. It's the way the hardware sees them. Note unsigned is effectively true, even though x86-64 uses canonical addressing. It still works fine if you use unsigned. I typecast pointers to the specific type I want to get at the point of usage, and I use a macro for that. So RW1 would give me a 16-bit 1-component value using a restricted pointer, and this macro supports 2 things. I can easily express a byte offset, for instance pointer plus 64K inside the parenthesis, and if I want to use a scaled indexed offset, I can also do that too, because instead of using the actual star, I use the bracket 0 bracket or the bracket index bracket in this case. You notice that this form is substantially smaller to see on the screen than what you'd get if you were just to write out the full C code without the macros and type defs. So for optimized pointers, I am using integer ops often, and I need to work with the original 64-bit pointer. Also note that in x86-64, opcodes only support scale offsets of 1, 2, 4, and 8 bytes. Anything else requires a hidden shifter multiply. I would like to avoid the shifter multiply when possible. I don't necessarily trust the compiler to do the right thing in optimization. It's better just to do it explicitly in the code. The example below is something that's very common. For instance, if you need to mask a pointer or if you need to align a pointer. Base in this case is forced to the beginning of a 4 kilobyte page, and wrapped below is wrapped to a 4 kilobyte ring buffer that is aligned at a 4 kilobyte boundary. When I need to use structures, I often just typecast the pointer to the structure to access a member, and I have some defines for that. So RT underscore will give me a restricted pointer to the specific type, X, and VT underscore will give me a volatile pointer to that type. Example below, when I want to access my structure T and member, I use the macros as shown below. Now we're going to enter the meat of this talk, the most important part. Generalized function pointers. Remember that typecasting from unsigned 32-bit to unsigned 64-bit and vice versa is free, and the returns are always put in RAX, so it's free to discard them, meaning I can always use a function pointer that provides a return even if I don't use it. RAX is a call or save volatile value, so I set up some type defs for function pointers. I use C for call, followed by the number of arguments. In order to make the typecast work well, I use a bunch of defines, C, the number, followed by the underscore. That enables me to avoid a level of parentheses, which I feel makes the code much easier to understand. To access a function pointer, you will eventually have a bunch of type defs for arguments or for the return, and I prefer not to see them all the time, so I create new defines for using the function pointers. These defines start with either an L or an I for a 64-bit or a 32-bit return respectively, followed by the C and the number of arguments, followed by the underscore, which means typedef. In this case, the first argument is always the function pointer, so I use those other macros first to turn it into a C function pointer, and then I do a call on that, and the arguments I convert to 64-bit. So this makes a very concise way to do a function call of any type that I typically use, meaning with integer arguments or integer returns. And remember again that the demotion or promotion between 64-bit and 32-bit for unsigned is totally free. So these are fully optimized. Another thing I like to simplify is imports. Instead of writing out all the types for all the functions I import, it'd be nice just to import a 64-bit value and use it at the call site with the macro to get whatever function I want. Unfortunately, as we'll see later, you actually need to do it as a function pointer when you do the imports. So for instance, if I'm using GCC and Win32, I have a define m underscore macro, which will include the function as an import. So then when I use the specific function, I'm always using the L or IC and then the number of arguments macros with the underscore. Now you might be saying that, yes, there is a problem here. And that is, what happens if you want to mix this code with somebody else's code and somebody else already included Win32? Then you have a potential problem, at least in MSVC, where the compiler has some bugs. Specifically, you'll get a warning that a symbol has been redefined, and if you try to use the make it a warning instead of an error feature, that typically is broken, at least in the version of MSVC I used last. Therefore, the workaround is if Win32 is already defined, then skip all these m underscore macros to do the import. Note, at the point where I use these functions, like create thread, exit thread, and sleep, I always use the typecast to the correct actual function, which means it will work whether it's included via Win32 include or I'm doing it with my simplified method. So let's validate this. We'll open up Compiler Explorer, write some source code, and in this case, I'll do a simple use of DLSim in Linux with standard C in GCC. Note, if you use DLSim with 0 for the module and DLOpen, you will get the symbol for DLOpen. So we can write this with two different ways. We can make it so that we use standard C, so we know what the regular compiler is doing. And then we can use this modified C that I like to use. There's two ways to define DLSim. One, we could use that m underscore macro, or two, we could use, say, C1, because that's what it is, a function call. Or we could use L1, 64-bit value. And you'll note that if I don't use the m macro, the m underscore macro, I don't get the right disassembly on the output. So unfortunately, the simplified form in this case, because we're doing dynamic linking inside the actual executable instead of using dlopen and dlsim, we have to follow the m underscore. Here's another example of doing it with the L1, and you'll note that it doesn't produce the right code. So when we're manually linking, we can actually use L1, of course. So for instance, if I'm doing Vulkan, I simply import all symbols as unsigned 64-bit values. I put them in one giant array, ordered by code usage order, so we get good cache access. In this case, I use s underscore for static inline, L1 for 64-bit single component, vk for the array name, and then vk underscore max for the maximum number in the array. At the call site, I can use the associated generic type via the macro. So for instance, if I want vk create compute pipelines, I know I need 6 arguments, and I know I want one return. If I'm going to use the return, it doesn't matter. However, I will define vk underscore pso as the index to the actual function pointer inside my vk array, and I will use the rl1 underscore to make it a restricted lookup when I actually look up the function pointer. This way, if I use it multiple times in a row, it could potentially be cached in a register without another lookup. So in the past, I would do type defs for all the functions, and then I would do some complicated large amount of C code to have my Vulkan include inside my source code, written with the types that I like to use. However, with the new system, I no longer need this mess anymore. It just goes away. It becomes very simple to use Vulkan without much overhead in the code. So if we look at an example below of working between Windows and Linux, you'll see that I can very easily include access to Win32 stuff without headers, simply by using the m underscore to bring in the Win32 function right before I use it, which is great. So all the information is consolidated onto one line, and it's very obvious what I'm doing. Note, while this project is not going to target C, I am still doing C work, both in my day job and in the project. Often it's nice to have a C version of everything for when you cannot use your own custom language. Other thing is, by rewriting these libraries a few times over the years, I learned new things. For instance, I had used futexes in Linux for a long time and never realized that Windows had added those interfaces in. You can use wake by address all and wait on address to do a futex in Windows. So in the future, I will continue to describe interfaces at a low level in C while I'm using them outside of C in my own projects. Anyway, that's it for this time.